Okay. Okay. So I don't know. I guess you heard that as well. Did you hear that?
Yes, that yeah. So
Yes.
got it.
Okay.
This meeting is being recorded, and I've got a
Okay.
big thing here.
Okay. All right. So, is it okay to start?
Yeah, I think so.
Okay, great. So it's a great pleasure to have Daniel Chan with us today from UNSW Sydney. So the title of Daniel's talk is The Minimal Model Program for Arithmetic Surfaces Enriched by a Browner Class.
Okay, thank you very much, Berouz, for the invitation to talk in this Zoom algebraic geometry seminar. As the title suggests, I want to talk about a version of the minimal model program. It's a version which, I mean, I'm kind of more non-commutative algebraic geometer, so I like to think of it as a non-commutative version of the minimal model program. But if you're more a straight algebraic geometer, you can also think of it as just minimal model program enriched by a Browne class. Okay, so let me just switch now to the actual, yeah, let me just shrink some things and I'll, yeah, and then I'll be able to go. Yeah, so let's start by what are the objects of interest in this talk. So I guess what I want to do is I want to think about perhaps what I can call a Browne log surface. Okay, so what's a Browne log surface? So that's going to be a pair x beta. And x here is going to be something I'll dub an arithmetic surface. And I'm going to use the term here in perhaps what is not the usual sense for an arithmetic surface, so I better define it properly. So firstly, this will just be a normal integral two-dimensional excellent scheme. And for technical reasons, I want it to be quasi-projective over some Noetherian affine scheme. So there's still a fair bit of flexibility in what that is. And the adjective arithmetic, I haven't put that bit in here yet. So let me just say what I mean by in what sense is it arithmetic? It's arithmetic in the sense that the residue fields, that such the residue fields here are finite. Okay, so I'll give examples of the typical types of things that I'll look at a little bit later, but this is the situation that we're looking at. So we can either work over a finite field, varieties over a finite field, or we're working in something over Z basically. Or more usually the L-adic integers. So K here I'll usually use to represent the function field of this arithmetic surface X. And beta will be an element of the Browne group of the function field. Okay, so I guess there are lots of ways that you can define this. So let me just give you two that will be kind of maybe helpful. So the first one is to think of this as just an étale cohomology group of the field of the multiplicative group. I guess the other way to think about this is that really it is the set of, this is probably the more usual way, and this is where the non-commutative algebra comes in. It's the set of central simple or K algebras. And you consider them, of course, up to some equivalence relation. And unfortunately, it's not isomorphism, but it's not too much worse than that. It's just Morita equivalence. Okay, so just some basic facts about this group. So firstly, it's an abelian group. And from the point of view of this second description here, the multiplication here is just given by a tensor product of central simple algebras. And the other thing is it's torsion group. So we can talk about the order of this element beta here. Okay, so we'll just enrich this arithmetic surface with this extra piece of data. And in this setting here, unfortunately, we'll need to put some extra assumptions on what this beta will be. And I'll put a bit more than usual just to make this talk a little bit more accessible. So the order P of this beta here, firstly, we'll make it a prime here. This isn't so important in general, but later on for the stronger results, I'll need it. And most importantly, I want it to be co-prime to the residue characteristics. And in fact, maybe I want something stronger. So in fact, we'll want this OX to contain some primitive p root of unity omega. Okay, so that's just some extra assumption that I'll just need. Okay, so if you haven't played around with the Brow group much, let me just tell you the type of examples that will be important for this talk. So the easiest way to get a central simple algebra, they're the symbols. So let me just tell you how you can get them. So you just pick two non-zero elements in this function field. And the symbol is often denoted like this, A, B, and we'll subscript it with this p-th root of unity. And the algebra is given by, you look at the non-commuting polynomial in two variables, x and y, and you just mod out by x to the p is equal to a. So that's one of the elements. Y to the p is equal to b. And then the non-commutative comes from the fact that, well, it's not too badly non-commutative. The y and the x skew commute. So yx is only equal to omega xy. And when you do this, you'll see that when you do get a finite dimensional algebra, it's quite easy to see that the dimension of this is going to be p squared over k. And so this will be a central simple K algebra. And that's the type of thing that I want to enrich this arithmetic surface well with. Okay, before I move on to the next slide, does anyone have any questions? Or actually, if anyone has any questions, just feel free to stop me, actually. Okay, but before I change the slide, I like to pause because I don't like to switch too quickly away from the slide. Okay, so to study this, this Brow class, we need some invariants, and the important invariant for us will be ramification. So we look at ramification at codimension 1 points, in other words, at irreducible divisors. So let's just pick an irreducible curve on this x. Since we assume that x is normal, there's some sort of discrete valuation ring at that curve C, so we can look at its associated valuation there. And to that C, you can talk about this ramification map. So let me tell you about this ramification map. AC goes from the Brow group. Okay, actually more, it doesn't quite do this, but I'll write morally what it should do, or what it almost does. And it maps to another atype cohomology group. You look now over the function field of this curve C, and the coefficients are in Q mod Z. Okay, so unfortunately, you don't quite have that. We have to look at the part which is, I'm going to put a prime here. And what this means is, just to state, this is the part which is prime to residue characteristics. Okay, so we just, and in fact, the most important part, if we just look at a beta here, which is order P, then you can just look at the P prime, P torsion part. Okay, so if you're not too familiar with this thing on the right-hand side, let me just say what this is in other terms. Another way to think about this is you can look at this as just the homomorphisms, I guess continuous, of the Galois group of the separable closure of this over K of C into Q mod Z. So of course, really you're just looking at homomorphisms from here to this. And so the image has to be a finite cyclic group. And so the important data that comes out of that is the kernel of this map. So basically what you'll find is you're really considering some finite cyclic quotient of this. So you're just looking at a cyclic extension of K of C. So the important information here essentially is that given this beta, okay, for each irreducible curve, you're going to get some sort of cyclic field extension. Okay, and there's a little bit more data that's involved, but that's the important thing. So I haven't defined this map, but you can do it various ways. I thought perhaps it's more important to see what happens in this particular example, so I can show you some examples of what's going on. And here it's quite simple to see what's going on. So let's do that right now. So the formula here, I'm just going to write it as a formula firstly. It has to involve the A and B, and it also involves this nu. So it's going to be -1 to the nu of A times nu of B. And then you look at A to the nu of B times B to the minus nu of A. And you restrict this to C. Okay, so let me just explain what's going on here in this formula. And so firstly, if you look at this, if you look at the valuation here of this thing here, because of the way you set it up, this has valuation 0. So in the discrete valuation ring, it's going to be a unit. So you can reduce modulo C to make it land inside K of C. I'll do an example later. We don't actually want to consider it inside K of C cross. We're going to remember there's a by the way, this algebra here has P torsion in the Brow group, this symbol. So we want to think of this as inside K of C cross modulo P times that group, or the P multiples in that group. So KC cross P. And the key thing is that in this case, this is actually isomorphic via comma theory to H1 K of C mu P. And that's kind of how you go from here to here up the top. Okay, so I'll do some examples in a little while so that you can really see what that means. But that's the basic ramification formula that I want to get across. So by the way, if you're wondering, this Brow group, what does it consist of? How close is it to these types of things? Well, basically, you can generate the Brow group using elements of this sort of form. Okay, so there are kind of two remarks that I want to make about this ramification. So the first one is that, when you look at this AC, the values inside here on this right-hand side, what you'll find is that it classifies cyclic extensions of the function field of that curve. So you can talk about ramification of that cyclic extension, and that's called secondary ramification. Okay, so you can look at AC of beta, classify cyclic extensions of this function field of the curve. So you can look at ramification of that. So ramification of ramification, that's secondary ramification. The other thing is kind of more of as a side, if you want to think of this in terms of the non-commutative algebra side of things, if you try to globalize the notion of essential simple algebra, you get an Azumaya algebra. So you can ask, does this come from an Azumaya algebra globally? And this AC basically measures the obstruction. AC beta measures obstruction to being Azumaya. Being a central simple algebra means Azumaya at the generic point of X. So you're wondering whether it's also Azumaya at the generic point of C. Okay, so that's that's why I've called this map A here. It's supposed to be obstruction to being Azumaya. So there's a sort of purity of branch locus. If X happens to be regular, then actually to be Azumaya, it just needs to be Azumaya at each codimension 1 point. Okay, so it does actually give you some sort of criterion for Azumaya. Okay, so the next thing I want to do is I want to try to link this up with the notion of a log variety and log surface, which is probably a lot more familiar with to people. And that makes it, I hope, of interest to algebraic geometers more generally. Okay. Actually, let me do an example so that it's a bit clearer what's going on. And then I'll link it up to the notion of a log variety. Okay, so let's see what's going on here. So in this, so firstly, we say beta ramifies along C if this AC of beta doesn't equal 0. This AC of beta lands in a torsion group. So in which case we say this ramification index along C is, well, we'll denote it with EC, that's a common notation for ramification index, is defined to be the order of AC beta. Okay, so it's in a torsion group and we can talk about its order. So let's do a little example. So let's pick something that's patently arithmetic. So we'll look at the L-adic integers here. And let's suppose that we throw in the pth root of unity. And so we'll look at the integral closure of R inside Q L hat omega. So we want a surface, so let's just pick the simplest one. So I'm just going to look at X is going to be spec of R W. So I guess this is the type of picture we'll kind of look at, a spec of R. And let's pick A to be an element of the R cross. Okay, and so what we do here is well, you have to pick a beta as well. So I'm going to retreat with a beta, and I'm just going to pick the symbol AW omega. Okay, we want to look at ramification here. So let me just say some words about the ramification when we try to compute this. So when we look at this ramification formula here, you'll note that if you want ramification, you'll need either this nu of B or this minus this nu of A to be non-zero. If you get zeros there, you just get one. Everything's just one here. So it's going to be trivial inside this group. So basically, you need to look for poles and zeros. So here, A is going to be a unit on the inside OX. So the only zero that's going to occur is where W equals is where that has zeros. Okay, so this only ramifies along. The only place where it can possibly ramify is where W equals 0. So maybe I'll put that in red. My C there. And so what's the ramification index there? So the way it works is essentially is just given by that the residue of A. So here and ramification index given by EC is going to be, well, essentially it's just comma theory. So it's the cyclic extension that you get by adjoining a pth root of A. That's the way you should think of it. Okay, so it's basically K of C, and you've joined a pth root of A to K of C. And this is what I mean by, yeah, you have some sort of a cyclic extension. So in this case here, you get this cyclic extension just adjoining a pth root of A. And this one here is just, well, I guess it depends on what A is, how big this cyclic extension will be, whether it's trivial or not, rather. And I guess the other thing I want to say about this cyclic extension is it's unramified. Okay, so if you want to look at secondary ramification, it's going to be unramified. Okay, there's yeah. Okay, so hopefully that example sort of gives you some sort of picture for what one should think of when you think about a brow log surface. Okay, so we have just some arithmetic surface like what you see here, and then you have something that's a brow group element like a symbol, and then the type of picture that you view is what you see here. Okay, the ramification is along this curve here, and there's this cyclic field extension that we think of as sitting on top of that. That's our picture of a brow log surface. Okay, so maybe we'll move on to the Next slide. So what's the associated log surface? So this is going to be the following. Firstly, we need a boundary. So the boundary is going to be just simply defined by you sum over all irreducible curves. The following quantity, it's a linear combination of those curves. It's going to be 1 minus 1 on EC. So most of the time, you're in the unramified case. So most of the time, this will be 1, and in which case this coefficient here will be 0. So that means that this is a finite sum. Okay, so that's a fact I guess I didn't write down, but it's, yeah, there's the number of ramification curves will be finite. And that also allows us to define the canonical divisor in this case. So kx beta is just equal to kx plus this delta x beta. And if you're wondering where this sort of definition comes from, I mean, the real motivation comes from looking at this in terms of the non-commutative algebra. So I don't want to dwell on this too much, but just to say some words about this. If you have this central simple algebra, you can try to globalize it and try to find some sort of integral model of this, so to speak, on X, the global arithmetic surface. And if you do this, what you'll find is that you'll get something which is generically Azumite. It's Azumite except at the ramification locus, and it's going to be, well, there's kind of an optimum one, more or less, which is called a maximal order. And you can talk about, well, what's said duality in that sort of context? And it turns out that you can define something which is like the canonical bundle. And this is the formula that kind of comes out of it. So there's a reason why there's this formula is the one it is. Okay, so the last thing that I want to say is, of course, I'll just introduce some notation, which hopefully will be clear. Now, if you have this Brauer log surface, you can attach this boundary, so you get a log surface. So that's the associated log surface. And now that we have that, actually, it turns out that we have all the definitions we really need to actually define the things in the minimal model program. Okay, so for example, if you want to define what's terminal, in fact, you can define discrepancy as well, and it'll be kind of clear from what I write how to do that. But I just wanted to define terminal, so just to show you. Okay, so how would you define the terminal? Okay, so what do you normally do? So if you want to check that something's terminal, you look at all proper birational maps. And in this case, will be from Y to X. And then you're going to compare the canonical divisor on Y and X. So in this case, note that Y also has the same function field as X. So you can also consider this Brauer group element as enriching the Y as well. So you can also talk about KY beta. Okay, so that's well defined. And then you want to write that up as F upper star of KX beta plus, and then there'll be some linear combination of exceptionals where EI are exceptional curves, and AI now, for it to be terminal, just means that these are all strictly positive. Okay, so that's kind of the natural thing that you would expect. Okay, and more generally, as I said, you can use these AIs, you can write this expression and use these AIs to define things like discrepancy. And then you can define also the notion of canonical and log terminal, if you like. So a priori, there's no reason why this should be an interesting thing, and I hope to convince you that this is indeed an interesting thing. So let's just compare with the notions that we have so far. So how different is this X beta, this Brauer log surface from the log surface? So the first thing is that if this associated log surface is terminal, it's quite easy to see that then this X beta is terminal. And if this x beta is terminal, then this log of this x beta is log terminal. So these implications aren't too difficult. The main thing is that, well, how different are these discrepancies, are these AIs from the usual ones that you get? So the main difference is that when you look at ky beta as opposed to the usual just ky, it may ramify on these exceptional curves. So the differences could come from things like this. So, and the coefficients are here are all between, well, I guess the smallest you could have is 1 minus 1 on 2 actually. So that's half. And the biggest is up to, but not including 1. So this x beta, well, firstly, it depends critically on the beta, and you can't get it from the log surface. It's somewhere kind of in between these two sort of notions, okay? But that at least gives you some sort of bound for talking about terminal, okay? So I guess the most important thing to have if you want to make sure that this program works is that you can, that terminal resolutions exist. And this is something that, oh, by the way, I should have said that this is all joint work with Colin Ingalls. So he's my co-author on this project. So terminal resolutions exist. Okay, maybe before, I'll just check to make sure there are no questions before I move off this slide. Yeah, so it's kind of nice that, yeah, at least we can define all the things that are involved in the minimal model program. And yeah, hopefully you can see that actually something interesting sort of comes out of this. Okay. Okay, so let's move on to an example of a terminal brow log surface, just to show you how it's kind of quite different from and exhibits some new phenomena that you wouldn't see otherwise. By the way, I guess this project, we've done the non-arithmetic, the sort of the geometric part where you work over an algebraically closed field quite some time ago. But for some reason, this arithmetic story introduces a lot of interesting sort of examples. And so in particular, this one involves Hirzebruch-Young singularity. And I mean, I've kind of only recently got into this, you know, mixed characteristic things lately. So my impression is that the notion of a Hirzebruch-Young singularity in this sort of context, it's not so well defined. So I better say exactly what I mean here. So essentially, the one I want to look at is just you contract a minus p curve. Okay, so let me just be more precise, perhaps. So f, let's say y to x. X here is just going to be the spectrum of some ring where Rm is tensor local. So E is contained inside here. And this E is, and that's the only thing that's contracted. And this E is a minus P curve. So E squared is minus P. Okay. So E is isomorphic to, it's a projective line. And I guess the other thing that you should know in my definition of a Hirzebruch singularity here is it's a projective line. It's also a projective line over the residue field of this R here. Okay, so there's no change of the residue field. So, so I also have to enrich this Hirzebruch-Young singularity with a Brauer class. And I'm just going to tell you that there exists a Brauer class beta of order P ramified on E only in Y. Let's draw a picture here. I don't know the best way to do this sort of thing. So here's my E, which is a minus P curve. And there's some sort of ramification there. And well, basically, when you check ramification, you just do it at, what do you call it? Yeah, on divisors. So there's no ramification down on X. Okay, it's not ramified along any curves on X. The only curves it's ramified on in this picture here is on the E upstairs. Okay, so there's my Y. There's my x. Okay, so let's just go through this example slowly and see what happens. So firstly, let's just do the usual, work out what the junction is for ky. We'll remind ourselves what it is. So in this case, it's f upper star kx plus, and it turns out to be 1 minus, I need to get this the right way around, 2 on p minus 1 e. So this is the formula. I guess you can check this easiest by you take the dot product of both sides with E, and then use the junction formula because E is isomorphic to a projective line here. Okay, so let's look at ky beta now. So if you want to look at this as the Brauer log surface, you want to look at ky beta, and the point here is that this is ky, and you have to add in the boundary that you get from the ramification here. So it ramifies on this E, and the ramification index here will have to be P. It turns out, so this is 1 minus P. And so if you just add these things together, what you find that this is kx. So in this case here, since there's no ramification along curves down on x, kx is the same as kx beta. So this is f upper star kx beta plus, and then you just add these two terms here. What you'll find is that, well, you'll get a 1 on p coming up here. So what's interesting in this example is that when you perform this proper birational map, okay, on X to try to resolve it, and you look at this adjunction, the coefficient that you get out here, okay, it's not negative like it was before. So this is usually negative unless p equals 2, okay, in which case that is 0. So it's never terminal. It's not regular anyway, so of course it's not terminal. But it's at best canonical and usually log terminal. But here, actually, because of this extra term here, this ramification which only occurs there, that kind of saves you, and that makes this coefficient positive. Okay, so this is kind of curious behavior. And in fact, what you'll find is that this, in fact, x beta is a terminal. Okay. So this is kind of curious, is that, you know, you have this Hertzsprung-Jung singularity, but you can put this rather interesting Brauer class on it that makes it actually terminal. Okay, so it's this Brauer class that's kind of, and the fact that it has this ramification along here, that's giving this extra term here, so that it can cancel with the negativity here, give you something positive, and that will actually make it sort of terminal. So I mean, when I started this project, I was thinking the type of behavior to expect is kind of similar with, you know, when you do surfaces in characteristic P and also over in mixed characteristic in an arithmetic setting. The theory is actually quite similar to the usual characteristic 0 setting. But here it seems to be, you know, really introduce a lot of new sorts of things. And this is one example I want to show you so that you can kind of see that, yeah, this is something that new that happens. So this is something that doesn't happen if you look at Brauer log surfaces, but you're only working over in characteristic 0 over an algebraically closed field. This won't happen. Okay. If you have terminal, in fact, the center, this x will also be terminal. But here in this setting here, you get some more interesting examples. So you may be wondering then, well, what are all these terminal pairs? Can you actually say what they are? And in general, we can't, but there is a case when we can. Okay, so I want to tell you about the case where we can, and this is the classification of terminal Brauer log surfaces. Okay, so this is also a theorem with my collaborator, Colin Ingalls. So we're going to look at this A-tile local setting. So Rm is going to be a Hensel local, and X will be the spectrum of that Hensel local ring. We'll have some Brauer class as usual. And this Brauer class now, it's going to be prime. And now we have to fix the order of this prime, this prime to be at least strictly greater than 5 rather. So this is a little bit unfortunate, but this is a condition that we have to impose. Then what does it mean to be x beta to be terminal? Can we sort of pin that down? And the answer is yes. In this case, we can really pin down what it means. So the first case, so it has to be exactly in one of these three categories. So the first case is where x is regular and beta is ramified on at most one curve. It can be either not ramified at all, or it can be ramified on one curve with multiplicity 1. So maybe the picture that I should draw here is like this, and there's a single curve with that. And that's because it's easy to see that's terminal, because in this case, the log surface is going to be terminal. The log surface terminal. So that means that x beta is also terminal. The second case is new even for the for Brauer log surfaces, and occurs also in the case where you're in characteristic 0. And that's where your beta is ramified on normal crossing. So it's ramified on normal crossing. But the thing that's going to save you is the fact that I mentioned this thing that you remember the ramification is really given by cyclic extensions of those curves. And so you can talk about that ramification. So there's secondary ramification. So, so what happens in this case, I don't want to dwell on this case so much just because it's kind of older stuff, but essentially you'll have some ramification of those two curves there. And where that ramification will occur is actually at the node point. Okay, so that's something that, that can happen. And the final situation as to what happens is a generalization of the last example that I gave. So they're the more general sorts of Hirzebruch-Junge singularities, okay, and where you have some sort of non-trivial Brauer class that sort of kind of saves you from being otherwise not terminal. Okay, so what do I mean by Hirzebruch-Junge singularity? I spelled that wrong. So in this case, the minimal resolution has a string of P1s for its exceptional curve. So the EI is a string of projective lines. And again, when I say a projective line, I mean this in the strictest sense. It's a projective line actually over the residue field downstairs of this X. Okay. And not just any Hirzebruch-Junge singularity. Okay, it has to be one of a very special type. Okay, so a natural invariant that you can attach to a Hirzebruch-Junge singularity is you can look at the associated matrix that gives you the intersection numbers, okay, and look at the determinant of that, or the negatives of that. So we look at this E1 squared, E2 squared, all the way down to whatever it is, E squared, and we put minus ones down here. So we need this to equal P, exactly the order of this Brauer class. Okay, you only just look at the ones where that equals P. And of course, you need the Brauer class to be non-trivial. And beta is ramified on all the EI, but no other curves. Okay, so it's a direct generalization of what we saw before. No, sorry. What did I do here? Yeah, it's negatives of everything. Yeah, negatives of everything. Yeah. So in the case that we saw before, the last slide, basically there was only one curve. So you just have you had a minus p curve. And so the determinant of that was p, and that's what you have there. Okay, and yeah, so this situation can occur, and in this situation you'll also get something which is terminal. Okay, so let me just move on to the say a little bit more about how this minimal model program works in this Brau enriched setting. I guess the other thing that you want to do is to do contractions, Mori contractions. So maybe our result here is not so optimal, but it's kind of, it has its own interests. I think the way that we've expressed it here. So suppose you're in a situation where you actually have a contraction of the surfaces first. Okay, so here you're contracting just a single irreducible curve E inside X. We say it's a Castelnuovo contraction. I guess we really should say with respect to beta and to the Brau class of both of them. If we're in the situation of the following lemma, okay, so if k x beta dot e is negative, so if you have a k negative curve where you use a canonical divisor now of this Brau log surface, then w beta is terminal. I should say, if x beta is terminal and you have this, so when can you contract the terminal to go to terminal? Okay, so if x beta is terminal and you have a k negative curve on there, E, then w beta is terminal. So I guess the thing that you'd like to know is what are all these possible Castelnuovo contractions? I mean, is there an analog of, you have these -1 curves, okay? And we do have that result. And this is also something a bit interesting because we get some examples that are kind of a bit weird. I don't want to write the list, but the theorem that I want to state here first, before I give you the interesting example, is the following. So again, we're going to work down the bottom. We'll be in the Hensel local situation. X is going to be spec R Hensel local. Beta is going to be prime of order 5. So if X beta is terminal, then there exists a unique Castelnuovo contraction. F from Y to X. And we do this actually by constructing them. Okay, so maybe I'll just say a little bit about what happens here. Yeah, so in this case, so maybe I'll go back up to the previous slide. So you may think, well, is the answer just a blow up? Well, it turns out that in this case here, if you have normal crossings, then the answer is you just blow up that point. That's the Castelnuovo. That will give you a Castelnuovo contraction, or the reverse of that. If you have no curve, of course, if there's no ramification curves, it's as you Meyer, then you just blow up the point. But actually, in this case here, if it is ramified on a curve, you will find that it's something a bit more interesting. Okay, and in this case here, it'll be even more interesting, but it's a little bit complicated to describe, so I don't want to describe it. So let me just do the example that I want to show you here. Okay, so this is the example. So you have the terminal order, which is ramified just on a single curve here, and there's no secondary ramification. So what's the picture of what this looks like? Okay, so in this case here, what you do is you'll have a, yeah, maybe I'll yeah. So what you'll find is that you'll have strict transform of that curve is here. There will be a single curve that you've contracted. So that's the E. But actually, this is not smooth. There's going to be here a Hertzsprung-Young singularity. Okay, so it turns out that that's going to, so it's going to be one of the ones that's in that third list of things. And if you're wondering what Hertzsprung-Young singularity will be there, this will, the minimal resolution of this has P minus 1 minus 2 curves. Okay, so it turns out that this is a Castelnuovo contraction, okay? This is something that will be basically kind of, by the previous slide, you can get examples of this being a terminal brow log surface, and you can contract this to this situation here. Okay, it turns out if you just blow up this point, and I'll show you this on the next slide, if you just blow up that point, you won't get something that's terminal. Okay, so this is something that's pretty weird as to the type of thing that can happen. Okay, so let's just go to this example at the end here, and hopefully show you a bit more of the type of phenomena, and also show you an example of how you run the minimal model program. Okay, so I'll keep an arithmetic example. So most of the results I stated before were for primes bigger than 5. And but one thing that is true is that all those examples I gave you, even for primes smaller than 5, they will be terminal. Okay, the only thing is that there could be more terminal brow log surfaces than the ones that I wrote there. So that's the thing that we don't know at the moment. Okay, so we're going to look similar to the situation that I had before. So it'll be something where you have a surface, okay, and it's going to be ramified on a single curve, multiplicity 1. And it's the kind of the example that I gave before. So you have Z hat L, and you join W, and you look at the spectrum of that. And then you want to make sure that you have, in this case, I want to look at the prime 3. So you want cube roots of unity. And I'll just insist that L is congruent to 1 mod 3, so there is a permitted cube root of unity there. And the brow class I want to look at is the one that I sort of looked at before. This is A comma W omega, where A is some sort of unit in this Z hat L. So in this case, you do find that you have, let me just change this. This C is going to be your ramification curve. And that's the only ramification curve. And we'll insist that this is a non-cube, so that there actually is ramification. And if you remember how this ramification works, we use this comma theory. Basically, you're joining a cube root of A. And so we look at this, we record that ramification as essentially this, you look at A modulo the cubes. Okay, so you're basically joining a cube root of A. And so you look at that modulo cube. Okay, so let's forget the brow class for a moment, and let's just randomly do some blowing up. Well, maybe, yeah, we'll just do a little bit of blowing up here and see what happens. Okay, so let's just blow up the close point on this curve. Okay, so we blow up the close point, and then what do we find? So we have a strict transform is here, and we also have a -1 curve that comes out. Okay, so we can record the ramification on the curve. So I'll put the given by alpha here. And if you remember the ramification formula that I told you for this, so what you do, the key point that I want to state is that, remember, the only place where it ramifies this, you need A or W to have a 0 or a pole. Now, A is going to be unit everywhere. So you just have to look at where the zeros of W are. So it used to be that the zeros of W were here, but now that you've blown up the point, there's a 0 here and there's a 0 there as well. So that means that it also ramifies here and here. Okay, so it ramifies the beta, when you pull it upstairs, it will ramify on both of them. Okay, so, and that's not on the list of terminal, and that means that actually this is not terminal. The brow log surface here is not terminal, which is why when we did the kind of the blow up on the previous slide, right, you have to have this strange sort of Hirzebruch-Young singularity. So that's no good. Okay, so let's blow up two more curves. Let's blow up another curve. Let's blow up this point here. Okay, so you'll get the this here, and you'll get a -1 curve in between. A -1 curve here, and a -2 curve over here. And again, the ramification that's going to be given by alpha on this one, and alpha, that old exceptional now becomes the -2 curve, that also has alpha. And the way the formula goes for working out what is the ramification here is that you kind of multiply these two, so you get alpha squared here. That's the way it works. So that's just something that happens here. And then, so this is not terminal either, because you have normal crossing, but if you have normal crossing of the ramification curves, then what you'll find is that you need secondary ramification. There's no secondary ramification here. All the cyclic covers are basically coming from residue field extensions. So I'm going to blow up two more curves, which is the nodal points here. And I get a final picture over here. So here's this original strict transform of the original ramification curve. I'll have a -1 curve here. Okay, so the old curves with this alpha here, -2 now becomes a -3 curve. The middle -2 that you've blown up 2 points, so that's a -3 curve. That's an alpha squared here. And then as for the two new -1 curves, see what happens is that you multiply the alpha and the alpha squared. And here, this is, this is order 3. So that's trivial now. So what you'll find is that if you look at the log surface, it's actually just ramified on the log surface is given just by those 3 curves here. Okay, the ramification has kind of disappeared on those -1 curves. And so actually this is the one that's terminal. This is terminal, okay? This is the situation that's terminal. So we have something that's a terminal brow log surface here and something that's a terminal brow log surface here. And you can try to run the minimal model program and see what happens. And the thing to note is that, well, you can't go this way, right? That's not terminal. So you do something else instead. Okay, so what do you do instead? So the key point is that, well, you note that this is a -3 curve, and you're allowed to have some Hirzebruch-Young singularities if you have ramification on that exceptional curve. Okay, so actually, it turns out that you can contract those two, and they're both Castelnuovo contractions. So you just contract both of them. Okay, so let's contract both of them. So that's what you get. And then you've got 2 other curves left. And I don't know the best way to write them, but I guess the key point is that this here and this here, those 2 points are now they're Hirzebruch-Young singularities that we get from contracting -3 curves. And this will actually be a terminal brow log surface. And then what do you do next? Well, it turns out that the next thing to contract is this one here. That turns out to be the next contraction that you have. So you have the original strict transform of that curve C, and you have another curve. And this is going to be another, you can contract that, the yellow one here, that yellow curve. And that will give you, it turns out, another Hertzsprung singularity. And it's the one that has 2 minus 2 curves. So if you think about that, by the way, I remember the allowed Hertzsprung singularities, you look at, you have 2 minus 2 curves. And then what do? You have minus 1, minus 1. If you look at the determinant, that's 4 minus 1 is 3. So that's the prime that you're looking at, right? That's the prime here, p equals 3. So we contracted some minus 3 curves. And the other types of things that you can have is 2 minus 2 curves. That's the only possibility when you're looking at p equals 3. And the final thing is that you can contract that curve to go back down here. That was the last Castelnuovo contraction that I mentioned. Okay. So, so this is the example that I think is rather interesting and shows you that, yeah, there's got to be something to it, because you get some sort of interesting example how, this is not the usual way you would normally, think about going from here to here, right? It's going through the lower road. But if you add this, you throw in this brow class, that's what it tells you is, that's how the minimal model program works in this sort of instance. Okay, so it's rather strange like that. Okay, so maybe what I do want to do is in the last slide is just to suggest, I guess the biggest thing that I haven't talked about at all is about the brow class. And the key point is that in all of this business is you have to know, well, how do you control the ramification of a brow class? Okay, what types of brow classes can occur? Okay, so they're not very arbitrary, they're quite restricted. So I wanted to kind of say just some words about that so that you can get some sort of feel of what goes on here. Okay, and the answer to this question is the Artin-Mumford sequence. And one of the things it allows us to do is to answer the question, for example, well, how do you find the ramification along exceptional curves? Okay, so I mean, I did it in this example by explicit sort of formula, but in general, you have to use this Artin-Mumford sequences, which is for the case of a regular arithmetic surface. And in this case, you have this sequence. Okay, the sequence goes as follows. You can go from the brow class, maps to the this brow class of the field, and then you have all the ramification maps here. So this is the direct sum over C of H1 et al. Okay, C Q mod Z. And then, oh, by the way, you should have primes everywhere, unfortunately. And then the last thing that you do is that you can talk about the ramification of, these are cyclic field extensions, so you can ramify at various points. So there's an extra map here. So you sum over all the points. I've already used P, so maybe I'll use points, the codimension 2 points. They'll land in naturally inside mu inverse. Well, I probably should have put a prime here. So this is a secondary ramification. And so it's a complex, but we can control the cohomology. But with cohomology, at H1 term only, which is, well, there's another map here which goes from H3 KX, no, sorry, H3X GM maps to H3, so this is all et al. The function field GM. So let me just basically say how we kind of use this. So essentially, the main thing is we're enriching by elements in here, but to a certain extent, the only information we use is what's in here. So the question is, what is the image of this brow class inside here? We want to know what types of ramification can occur, right? So that you can compute discrepancies and what have you. And so all you need to do is, firstly, you look at the kernel of this map from here to here. And then there's some cohomology. So you have to have a secondary obstruction. You have to make sure that this second obstruction inside here also vanishes. So you have to control what are the possibilities there. Okay, I think that I'm out of time, and that's where I wanted to stop anyway. So thank you very much for listening.
Great. Thank you very much, Daniel. Thank you. Okay, all right. So do we have any questions? Are there any questions? Okay, well, if not, I'll ask a question. So what, so other, so I mean, I have a bunch of questions. So do you have is there like a cone theorem, or do you expect something like a cone theorem? Does it even make sense to talk about a cone theorem?
Yeah, so I'm just trying to think of the best way to sort of state what happens here. Actually, yeah, I think I probably need to think a little bit more about that. So that's yeah, that's a little bit.
I mean, it's probably not. I mean, I'm just from a naive look. It doesn't. You probably cannot just naively translate whatever is known in positive characteristic log setting and then get a cone theorem
Yeah,
here.
there are definitely things that are somewhat subtle about what goes on. Yeah, but this is. But we were quite surprised to see how much you can actually go through. Yeah,
right. Because the other thing that looks a little bit worrying is, I don't know, I'm not sure. So I mean, even if there's a cone type theorem, would you expect that this sort of canonical ring is somehow preserved? Because it seems like you have blowups that, you get dwarf singularity. So the negativity lemma is definitely not there. So I'm sort of wondering if you can even expect the canonical ring to be preserved under contractions in general.
Yeah, so you can. Yeah, so there are various canonical rings that are kind of floating around. And in some sense, the more sort of sensible one to use is you actually look on the non-commutative algebra, because there's actually a non-commutative algebra that you can associate to all these Brown log pairs, okay? Not uniquely. So you can actually associate these, basically they're maximal order. So it's essentially like an Azure-Meyer algebra, except the ramification locus, so a little bit some sort of continuation of an Azure-Meyer algebra. And since you have an algebra, you can ask, look for what would be an analog of the canonical bundle in that setting, and it's going to be a bimodule over that algebra.
I see.
And you can look at the canonical ring there. So that's something that we've looked at somewhat. That's a little bit tricky, actually, what goes on there. So I think probably we've thought more about that kind of thing. But yeah, you can also look at the, just the usual thing like the 5 years. Just trying to think. I think probably there is an answer to your question, but I can't think of it off the top of my head.
I see, sure.
So probably it's probably not explicitly written down, but yeah, we've probably got enough material to try to answer the question.
Right. Okay. Great. Okay. So, any questions? If there are no other questions, well, let's thank Daniel again for the great talk. Thank you very much, Daniel. And I know it's pretty early in the morning here, so yeah. So thank you for accepting to go talk here now. Okay, so I'll stop recording, which is the most important thing that I'm supposed to do. Stop.